Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel, and in today's video we are going to pick up the second part of how to find out the limits of indeterminate form functions with the help of L'Hopital's rule. In the first video of mine, you can see the link in the description box below. We studied how to figure out the indeterminate form of first type, that was 0 by 0. Here in this video, we are going to pick up those functions which on applying the limit are giving us this form. So how to get rid of this type of indeterminate form, that's what we are going to study or we try to understand here in this video. So I pick up few examples here with the help of which we are going to understand how to apply L'Hopital's rule on such kind of functions which after applying the limit give you infinity upon infinity form. So here you go, first of the example. Here you go. So you see, if in the beginning, if I try to apply the limit on this initial function, then it is going to give me indeterminate form of infinity upon infinity. Like in rough form, roughly if I just try to do the work here, for example, I try to apply the limit here, then you see tangent of 90 degrees or pi by 2 rads is infinity, and tangent of your 3 pi by 2 rads or 270 degree is also giving you infinity. So we are still having a form of infinity upon infinity here. We don't want this. So now, in the first step, what we do, we are going to take the derivative of our numerator and denominator individually, and then we are going to apply the limit over there once again. And then we'll check, has the problem been solved or still the indeterminate form persists. So you see, the derivative of your tangent x is sec square x. You are well aware about how to find out the derivatives. You're standing at the advanced position, of course. So there's no need to tell you the basic derivative formulas. And the derivative of your tangent of 3x is actually secant square 3x, and then you apply derivative or chain rule on this angle form. So it is going to provide you 3x, 3 here, alright? So the limit of your x tending to pi by 2 secant square x upon 3 secant square 3x. Now once when we try to check the limit, we just apply the limit here. So you see secant square of pi by 2 upon 3 times secant square of 3 pi by 2. Now we know that the secant is actually a reciprocal of your cosine, so we know that we can write it like this. It's 1 upon cos square of pi by 2, and this is 1 upon or 3 upon cos square of 3 pi by 2. So that's quite obvious. You can see cos of 90 degree is 0, so 1 upon 0 is infinity, and over here in the denominator it's 3 upon 0. 3 upon 0 is also infinity, because you see cosine of 270 is 0, right? So 3 upon 0 is infinity. So we are still having indeterminate form. It's still persisting. Okay. So what we do, we are once again going to take out the derivative of this numerator and this denominator individually. Alright, and let's see whether it is going to help us out or not. So let's try to do it a little here. We just write the limit as it is. And now we are going to take out the derivative of our sec square of sec square x. So what it is going to be here, first of all, I just recommend that we just take out this this denominator 3 outside before solving it out further ahead. So we just try to make it as simple as possible here. So I just write it like this, okay. And now you know that secant square is actually 1 upon cos square x, and it is getting, this thing is getting divided with this thing, right? That's quite obvious, I know, but I just try to, I prefer to speak it up. So you see, it is getting divided with this sec squared 3x, which is 1 upon cosine square of 3x, right? That's it. And now you see, once when I convert this or turn this division sign into multiplication, then the term which is written at the right side of your division sign will be written in the reciprocal form. That's quite basic maths. So we are just using it to get a simple form of function. So we're just trying our level best to turn it out. So you see, that's how it is going to be. Alright, so now we are going to take the derivative of this numerator and the denominator. So it's going to be 1 upon 3 x tending to pi by 2. And now you see, once when we try to apply the limit here, once when we try to take out the derivative of the numerator, what it is going to be? It is going to be 2 times cos of 3x, right? And then we take out the derivative of cos of 3x, which is going to be sine of 3x, yeah? And then we are going to find out our derivative of 3x with respect to the chain rule, so it is going to be 3, right? And similarly, we are going to take out the derivative of denominator, so it will be 2 times cos of x, and then we take the chain rule on, we apply the chain rule on cos of x, it's going to give me sine of x. Okay, so you see, comparatively, this 2 and this 2 gets cancelled, and this 3 is going to cancel this 3. So now what we have, the function that we are having now is this. Limit x is tending towards pi by 2, and it is cos of 3x sine of 3x upon cos x and sine x. Alright, so now you see, we have studied while discussing the functions. We know that if you're having a product of function, then the limit which is so applied on a product of two functions can be written as the product of limits applied on these individual functions. It can be written like this. Okay, both behaviors are going to give you the same result. So you see, if I just try to break this function, in this form, it's making sense quite well. My arrows are quite horrible, but I hope you can compromise on that. So this is it. You can write it like this. Now once when we apply the limit on these two functions which are so separated, does the indeterminate form still persisting or not? Let's see. So once when I apply the limit here, what it is giving me? It is giving me this form is still indeterminate, because you see cos of 3 pi by 2 upon cos of pi by 2. So this thing is still 0 by 0, right? So this portion is still in indeterminate form, whereas this part of the limit is giving me a definite answer, because you see sine of 3 pi by 2 or sine of 270 is -1, and sine of 90 is 1. So it is collectively giving me -1 answer. So here this thing has been figured out, but this portion is still in indeterminate form. So what we do, we are going to take out the derivative of this portion once again, or this part of function once again. So it is going to be cosine. The derivative of cosine is sine, yeah, and then we apply here chain rule on my 3x, so it is giving me 3, and then cosine derivative is sine x, and this thing is -1, yeah. So now what is left, I just write -3 outside, and then I'm once again going to apply the limit and check, has the problem been solved or still the indeterminate form is there. So you see, sine of 3 pi by 2 upon sine of pi by 2. Now you see sine of 270 is -1, sine of 90 is 1, so collectively I'm having -1. So you see now, finally, after applying the limit, I'm having a definite answer. So at last I just got a final answer which is quite definite and unique, and in the form of a real number, right? So that's how you keep on solving until you just got a definite answer. So that's what your lopital has been suggested, and that's what we have just applied. Okay, now let's see one more example, and it's also quite interesting. So another example, I just pick up question number 2. So another example is if I say limit is x is tending towards 0 and is natural log of x squared upon cotangent of x squared. You know, cotangent is the reciprocal of your tangent function, and my L is quite confusing, so I'm going to rewrite it. So this is my ln, a natural log. Okay, now if I just directly apply my limit on my numerator and denominator function, let's see what I get. I'm getting cotangent of 0 square. 0 square is 0, so it is actually ln of my 0, and it is 1 upon tangent of 0, right? So this is it. So you see, the natural function or natural log of your 0 is 0. You can see here, right? It is giving me an error. And similarly, if I just try to find out tangent of 0, the tangent of my 0 is giving me 0, right? But keep this thing in mind, and then we just come back here. So it is an infinity, and this is 1 upon 0, so this is also infinity. So we are having form indeterminate here. We don't want it. So now what we do, we are going to take out the derivative of my numerator and denominator, as we have done already in the first example. We just keep on applying that. Let's see how long it goes. So you see, the derivative of your logarithmic function is the reciprocal of the argument, so it is like that. And then you take the derivative of your x squared, so it becomes 2x. So, and here in cot of x squared, so cotangent derivative is negative cosec, right? So you can either write cosec or CSC, it's your choice. And then you take out the chain rule on your x squared, gives you 2x. Alright, it's like that. Now we just try to solve, or we try to simplify this function. So you see, I can cancel out this 2x this 2x is getting cancelled, right? So 1 upon x squared is getting divided with minus cosec of x squared here. So it is actually getting multiplied with 1 upon cosec squared, would give you sine x, the sine square, sine x squared, just like that. So okay, it's my bad, I just messed up with the formula. But the derivative of your cot is negative cosec square, not simply cosec. It's my bad, but I just rectify here. So okay, so the form that we are having here, the form of a function before applying the limit, it is 1 upon x squared getting divided with minus 1 upon sine square x squared. Yeah, so after further solving, the form that I'm having, I can write my negative sign outside here. So it is giving me sine square x squared upon x squared. Alright, so this is it. Now once again, if I just try to apply the limit here, let's see if it has been solved or not, or still the indeterminate form is there. Let's check it out. So once when I try to apply the limit here, sine square 0 square upon 0 square. So you see sine 0 is 0 and 0 square is 0. So I'm having indeterminate form this. That's what I'm having here. So I don't want it. So once again I'm going to take out the derivative of my numerator and denominator. So sine square x squared. So before applying the derivative for your a's, you can write the power on your sine function in overall sense, and then you take out the derivative. Okay, it's much better for you. And if you're too much in practice, then you can do directly as well. So okay, now you just apply the derivative. So you are going to use the derivative of a polynomial function xn first of all. So here it's become 2 times sine of x squared. Then you take out the chain rule on your sine x squared. It becomes cosine of x squared, and then you take out the derivative on your x squared. That's what the chain rule is. It becomes 2x upon derivative of x squared is 2x. Simple as that. So this 2x and this 2x gets cancelled, and what we are having here is sine x squared cos x squared, and 2 is going to be written outside. Alright, so that's what we are having. And that now once when I apply the limit here, you see sine 0 square and cosine 0 square. So sine 0 square is 0, cosine 0 is 1, so on multiplication it's giving me 0. So minus 2 into 0, it's giving me 0, and 0 is a nice real number. We are having a definite answer now. We stop our L'Hospital rule application, and we just stop our answer. We just stop further steps, and this is what we call the answer is. So that's how we apply the L'Hospital's rule. Let's see one more example and last example, and then it'll be quite more than enough. So let's see one more example here. Okay, so this is another example. We are having natural log of x minus a and upon natural log of exponential x minus exponential a, and limit is tending towards a here. So if we directly apply the limit here, so it is giving me ln of a minus a upon ln of e power a minus e power a. So both, you see, it is giving me ln of 0 upon ln of 0, and as I told you already that the natural log of your 0 is 0. You can see here once again that natural log of your 0 is giving you error, and error means infinity. I'm not using Casio calculator right now, I lost the software. So this is it. So you see the first form that I'm having here on after directly applying the limit is this, infinity upon infinity. So I don't want this. So what you do now, you're good enough to analyze that you need to apply the L'Hopital's rule. So we just take our derivative of numerator, so ln of this function, so it becomes the reciprocal of this function, and then you take out the derivative of this function as a chain rule, right? In the previous two examples I didn't show you the chain rule, but over here I'm just showing you. It's just for the sake of getting too exhaustive here, so it's like that. And then over here the derivative of your denominator ln is 1 upon this function, and then you apply the chain rule over here once again. Alright, and you see, just keep this thing in mind that a is a constant number here. Alright, so once when you apply the derivative here, derivative of your x is 1, derivative of your constant number is 0, and then you just move down, you just copy this thing as it is. Now you come over here, derivative of your e of x is e of x, derivative of a constant number ea is 0. I hope it's clear. So now we just keep on simplifying this thing. Now you see, it's 1 upon x minus a, and it is getting divided with ex, or exponential x upon ex minus ea, right? So it is showing me that if I just convert this division sign into multiplication, it is going to overturn the term which is on the right side of it. So it is going to be written something like this. Yeah, that's how it is. So the proper function that I can see here now after a nice simplification is, as I told you, my arrows are too worst. So anyway, so that's what I'm having here. It's ex times x minus a. Now what happens if I apply the limit on this function form? Is it giving me a nice definite answer or not? So e of a minus e power a upon e power a times a minus a. Okay, so you see, again I'm having indeterminate form. Alright, so I don't want this. I'm once again going to do what? I'm once again going to take the derivative of these numerator and denominator functions. So you see, in the numerator I'm having quite simple case, but in the denominator I'm having product of two functions, this exponential ex and this polynomial x minus a. So we are going to take the formula of product of derivative of product of functions. Keep this thing in mind. So once when I take the derivative of my ex, I'm getting ex back, and the derivative of my this constant number ea is 0. Okay, upon, now I'm going to use here the derivative of product of two functions, so it is going to be something like this. That's what I'm having. Okay, so it's going to be limit x is tending towards a. I'm having ex in the numerator simply. In the denominator I'm having ex of derivative of x is 1, derivative of constant number is 0, plus derivative of ex is ex itself, x minus a. Alright, now we are having this form. We once again going to apply the limit and check what we are having now. Okay, before applying the limit, it's much better if you just take out this ex common outside from the denominator, and that common exponential is going to be cancelled by the denominator exponential, right? So we can do that, becomes much easier then. So that's what we are having. And after cancelling these ex, we just cancel it. We are having simply 1 above, and that's what we are having now. Now we apply the limit. So once when we apply the limit, we are having 1 plus 1 plus, I'm sorry, at the place of x I just write a. It's a minus a. So this and this gets cancelled. Simply 1 is the answer. So after applying the limit, I'm having one answer, which is a definite number. It's a very, very nice real number. So we just got it. So that's how we just keep on applying the L'Hopital's rule till we just get a definite answer or an answer in a real number after applying the limit. So that's the way how we figure out the indeterminate forms. So inshallah, in the third series, in the third part of this series, we are going to check out the third indeterminate form, which is infinity minus 0 or 0 minus infinity, and we are going to discuss the related examples then. So that's all for today, and if you find this video helpful, please subscribe my channel, hit on the like, and share this video as much as you can with your friends and other learners. I'll see you inshallah with the next video very soon. Till then, just take care of yourself. Allah Hafiz.